Space has always captured humanity's collective imagination. From ancient civilizations who mapped constellations to modern astronomers probing distant galaxies, we've always looked up with wonder. Among the countless celestial bodies that have fascinated us throughout history, the planets of our solar system hold a special place. Each one a unique world with its own remarkable story. Have you ever wondered what secrets lie hidden in the darkest corners of our solar system? What cosmic horrors and breathtaking wonders exist beyond our familiar blue planet? I'm your host, and today we're embarking on a journey to explore the most extreme and mind-bending worlds orbiting our sun. Before we dive in, let me ask you something. Did you know that there's a planet where it rains diamonds? Or a world with winds 5 times faster than the most violent hurricanes on Earth? How about a planet hot enough to melt lead, where a day lasts longer than a year? Our solar system is far stranger than most people realize. Each planet tells a unique story of cosmic violence, extreme physics, and evolutionary paths that diverged billions of years ago. And the more we learn about these alien worlds, the more we appreciate the remarkable nature of our own planet. Today's journey will take you from scorching hellscapes to frozen wastelands, from violent gas giants to mysterious ice worlds. You'll discover phenomena so extreme they seem impossible, yet they exist right in our cosmic backyard. If you've ever gazed up at the night sky and felt that sense of wonder about what's out there, this video is for you. By the end, you'll see our solar system with entirely new eyes, understanding the incredible diversity and extremes that exist among our planetary neighbors. And here's something to consider as we begin. Everything we'll discuss today helps scientists in their quest to answer one of humanity's most profound questions. Are we alone in the universe? By understanding the incredible diversity of worlds in our own solar system, we gain vital clues about where and how life might exist elsewhere. Over the next hour, we'll explore worlds of fire and ice, storms larger than Earth, oceans of liquid methane, and planets that rain diamonds. We'll uncover how these worlds formed, how they've evolved, and what they can teach us about our place in the cosmos. So settle in as we explore the most fascinating, extreme, and terrifying planets that share our star. I promise you won't look at the night sky the same way again. Our journey begins with Jupiter, the undisputed titan of our solar system. Among the pantheon of celestial bodies that have fascinated humanity, Jupiter stands out as the largest planet in our solar system, its vibrant stripes and prominent great red spot making it easily recognizable. But there's far more to Jupiter than its size and famous storm, and our knowledge has grown exponentially with advancements in space technology and exploration. Jupiter is a gas giant consisting mostly of hydrogen and helium. Its diameter is approximately 11 times that of Earth, and it's so large that over 1,300 Earths could fit inside it. Despite its enormous size, Jupiter has the shortest day of all the planets, rotating on its axis every 9.9 hours. This rapid rotation creates powerful forces within the planet, generating the strongest magnetic field of any planet in the solar system. What makes Jupiter truly remarkable is its great red spot, a storm so massive it could engulf our entire planet with room to spare. At its widest point, it stretches about 1.3 times the diameter of Earth. This colossal hurricane has been raging for at least 300 years, with winds exceeding 400 miles per hour. Historical records suggest its existence dating back to at least the late 17th century, making it perhaps the longest-lasting storm in the solar system. The Great Red Spot is located in Jupiter's southern hemisphere, nestled within a westward-moving jet stream called the South Equatorial Belt. The striking red color remains something of a mystery to scientists. Current theories suggest it might come from complex organic molecules, red phosphorus, or possibly compounds containing sulfur. The exact chemical reactions that give the spot its vivid color continue to puzzle researchers despite decades of study. The storm rotates counterclockwise with a period of about 6 days. Interestingly, the rotation speed, size, and color of the spot can change over time, reflecting the storm's complex interaction with its surroundings. Recent observations show that the Great Red Spot has been shrinking, though it remains an enormous and powerful feature of Jupiter's atmosphere. Jupiter's atmosphere is a swirling cauldron of chemical reactions, creating the stunning bands of color we observe. These famous bands are actually high and low-pressure zones characterized by different types of clouds. The lighter-colored regions represent high-pressure zones filled with ammonia crystals, while the darker bands are low-pressure areas with complex chemistry creating reddish, brownish, and yellowish hues. When NASA's Galileo probe plunged into Jupiter's atmosphere in December 1995, it experienced the full fury of this alien world. Descending at an initial speed of 160,000 miles per hour, the probe transmitted data for 58 minutes before being crushed by the immense pressures. It measured pressures 23 times higher than Earth's and temperatures exceeding 300 degrees Fahrenheit before being destroyed. The probe never reached a solid surface because Jupiter likely doesn't have one in the conventional sense, just increasingly dense layers of hydrogen being squeezed into exotic states of matter. The longevity of Jupiter's storms, particularly the Great Red Spot, is intriguing. While storms on Earth last for days or weeks at most, Jupiter's storms persist for centuries. This remarkable stability is likely due to Jupiter's rapid rotation and lack of a solid surface, which minimizes frictional dissipation of the storm's energy. Without solid land to slow it down, and with an endless supply of energy from Jupiter's internal heat and the Sun, the Great Red Spot continues its relentless circulation. Jupiter's magnetic field is truly extraordinary, 20,000 times stronger than Earth's, and so vast it reaches all the way to Saturn, over 400 million miles away. This massive magnetic field creates intense radiation belts that would deliver a lethal dose to an unprotected human in minutes. The interaction between Jupiter's magnetic field and its innermost moon Io creates powerful electrical currents and spectacular auroras at Jupiter's poles. The gas giant's influence extends to its remarkable family of moons. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is a fascinating world in its own right. Io is the most volcanically active body in the solar system, its surface covered in sulfur and sulfur dioxide, giving it a colorful, mottled appearance. Hundreds of active volcanoes continually reshape its surface, spewing plumes of material hundreds of miles into space. These eruptions are driven by Jupiter's powerful gravitational forces, which flex and heat Io's interior. Europa has a crust of ice, and scientists believe it harbors a vast subsurface ocean containing more water than all of Earth's oceans combined. This makes it one of the most promising places to search for extraterrestrial life in our solar system. Recent observations have detected water plumes erupting from Europa's surface, providing potential access to this hidden ocean. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. Larger than the planet Mercury, Ganymede may also contain a subsurface saltwater ocean beneath its icy crust. Callisto, characterized by an extremely cratered surface, is believed to be the most heavily cratered object in the solar system, preserving a record of the early solar system. Like its siblings, Callisto may also harbor a subsurface ocean. Jupiter has at least 79 known moons, with more potentially waiting to be discovered. Many of these are small, irregular bodies captured by Jupiter's gravity, forming families of moons with similar orbital characteristics. Though Saturn is more famous for its rings, Jupiter also has a ring system, though much fainter and smaller. Composed mainly of dust particles from impacts on the planet's small innermost moons, these rings were first discovered by NASA's Voyager 1 spacecraft in 1979. Unlike Saturn's icy rings, Jupiter's rings are primarily made of dust, making them much harder to see. The study of Jupiter has come a long way since Galileo's first observations. Multiple missions have been sent to Jupiter to study its composition, magnetic field, and moons. Pioneer 10 and 11 were the first spacecraft to make a close approach to Jupiter in the early 1970s, providing valuable data about its radiation belts, magnetic field, and some moons. Voyager 1 and 2 made significant discoveries during their flybys in 1979, such as detecting Jupiter's rings and confirming Eo's volcanic activity. The Galileo mission spent 8 years studying the planet and its moons from 1995 to 2003, and its atmospheric probe made a direct plunge into Jupiter's atmosphere, providing the first direct measurements of its composition. The Juno mission, which arrived at Jupiter in 2016, continues to study the planet's interior structure, atmosphere, and magnetosphere. It has provided stunning close-up images of Jupiter's clouds and poles, revealing storm structures and dynamics never seen before. As we continue to explore Jupiter through telescopic observations and space missions, we unravel the secrets of this magnificent world, enriching our understanding of planetary formation and evolution. Jupiter stands as a testament to the intricate, diverse, and vast nature of our solar system, a cosmic giant that continues to inspire awe and scientific curiosity. Next, we travel to Venus, often called Earth's twin due to its similar size and composition. Venus is nearly identical to Earth in size, making it one of our most similar neighbors in the solar system. With a mean radius of about 3,760 miles, 6,052 kilometers, it's approximately 95% the size of Earth. Its mass is about 81.5% that of Earth, giving it a comparable density to our planet, approximately 5.24 grams per cubic centimeter, implying a similar rock-iron composition. But that's where the similarities end. Venus is a cautionary tale of planetary evolution gone wrong, a world transformed by a runaway greenhouse effect into one of the most hostile environments imaginable. The Venusian atmosphere is a crushing blanket of carbon dioxide 90 times denser than Earth's atmosphere. If you could stand on its surface, which you couldn't without being instantly crushed, you'd feel pressure equivalent to being 3,000 feet underwater on Earth. This immense pressure is enough to instantly crush most spacecraft that attempt to land there. Venus is the hottest planet in our solar system, with surface temperatures averaging 867 degrees Fahrenheit, 464 degrees Celsius, hot enough to melt lead. This scorching heat is the result of the most extreme greenhouse effect in the solar system. The high concentration of carbon dioxide in Venus's atmosphere traps heat energy radiated from the sun, preventing it from escaping back into space. There's very little temperature variation between day and night, or between the equator and the poles due to the thick atmosphere's efficient heat distribution, resulting in a virtually constant furnace-like temperature across the entire planet. The rotation of Venus is one of its most bizarre characteristics. Unlike most other planets which spin on their axis in the same direction as their orbit around the Sun, Venus rotates in the opposite direction, a phenomenon known as retrograde rotation. This peculiar behavior isn't yet fully understood by scientists, but some believe it may be due to a massive collision with another celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly, with a sidereal day, a full rotation on its axis, taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field, leaving its atmosphere vulnerable to erosion by the solar wind. Another quirk of Venus's rotation is that a solar day on Venus, the time from one sunrise to the next, is shorter than its sidereal day due to its retrograde rotation. The solar day on Venus is about 116.75 Earth days, while the planet's year, the time it takes to orbit the Sun, is about 225 Earth days. This makes Venus one of the few places where a day is longer than a year. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that completely enshroud the planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus appears so bright when viewed from Earth. The clouds are composed primarily of sulfuric acid droplets, an incredibly corrosive substance that would dissolve human tissue on contact. These yellowish clouds create a hellish environment where lightning flashes through acid skies above a scorched landscape. The atmosphere of Venus is arranged in several distinct layers. The troposphere extends from the surface to about 40 miles up. The mesosphere stretches from the top of the troposphere to about 56 miles high, and the thermosphere reaches up to 125 miles above the planet's surface. Above this, there's a transitional region called the exosphere that merges with the void of space. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few miles per hour. Venus's surface has remained largely mysterious for much of human history because its thick clouds prevent direct optical observation. However, radar mapping has revealed a landscape dominated by volcanic features. The planet has more volcanoes than any other in our solar system. Thousands dot its surface, ranging from less than a mile to over 150 miles, 240 kilometers, in diameter. Venus's surface appears to be geologically young, with a relatively low number of impact craters indicating a surface age between 300 million and 600 million years. Scientists believe that Venus undergoes a cyclical process where heat from the planet's interior causes the surface to be completely repaved in global resurfacing events. Despite the apparent geological activity, Venus doesn't experience significant plate tectonics like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity, or because its crust is too hot and flexible to break into plates. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all contributed significantly to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology, showing a world dominated by volcanic plains, highland regions, and distinctive circular structures called coronae, formed by upwelling of hot material from the mantle. Despite the challenges posed by Venus's harsh conditions, scientists remain interested in further exploring the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Venus, our neighboring planet, serves as both a warning and an opportunity. It shows us how a world similar to our own can become uninhabitable through a runaway greenhouse effect, a sobering reminder as we face climate change on Earth. Yet it also presents a fascinating laboratory for understanding planetary evolution and atmospheric dynamics. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of terrestrial planets and provide valuable context for interpreting the growing catalog of Venus-like exoplanets being discovered around other stars. Our journey continues to Mars, the red planet that has captivated human imagination for centuries. Once thought to host canals built by an advanced civilization, we now know Mars as a frigid desert world with a haunting beauty all its own. What makes Mars fascinating is the growing evidence that it once looked much more like Earth. Mars wasn't always the dry, barren place we see today. NASA's rovers have discovered conclusive proof that liquid water once flowed across the Martian surface, carving valleys, filling lakes, and possibly even creating a shallow northern ocean. So, what happened to transform this potentially habitable world into the frozen desert we see today? Mars's small size, just half Earth's diameter, caused its interior to cool faster than our planet's. As its molten core solidified, Mars lost its protective magnetic field. Early in the planet's history, Mars apparently had a strong magnetic field, likely generated in the same way as Earth's, through the movement of molten metal in its core. Because Mars is smaller than Earth, it lost heat more quickly, and its liquid core eventually solidified. When that happened, the convection stopped, the flow ceased, and the magnetic field disappeared. Without this invisible shield, the solar wind, a stream of charged particles from the sun, stripped away most of the Martian atmosphere, transforming a potentially habitable world into the barren landscape we see today. The solar wind is normally deflected by a planet's magnetic field, which prevents it from eroding the atmosphere. When Mars lost its magnetic field, the solar wind began directly impacting the upper atmosphere, gradually stripping it away over billions of years. The Martian atmosphere is now just 1% as dense as Earth's, too thin for liquid water to exist on the surface. This thin atmosphere also means extreme temperature swings, from a relatively mild 70 degrees Fahrenheit, 20 degrees Celsius, during the day near the equator, to a bone-chilling minus 100 degrees Fahrenheit, minus 73 degrees Celsius at night. Without a thick atmosphere to redistribute heat, Mars experiences much more extreme temperature variations than Earth. Mars hosts the largest volcano in the solar system, Olympus Mons, standing 3 times taller than Mount Everest. The planet also features Valles Marineris, a vast canyon system that would stretch from New York to California if placed on Earth. These dramatic features tell the story of Mars's geological history, a planet that was once volcanically active but has since cooled and become relatively dormant. The surface of Mars shows evidence of a complex geological history. We can see signs of ancient riverbeds, lake basins, and flood channels. The northern hemisphere has low, flat plains, while the southern hemisphere is mountainous and heavily cratered. This striking difference between the two hemispheres might be the result of a massive impact early in Mars's history, which blew away much of the crust in the northern hemisphere. Mars is a planet of dust and iron oxide, giving it its characteristic red color. Global dust storms can occasionally shroud the entire planet, lasting for weeks or even months. These storms can be so massive that they've occasionally forced NASA's solar-powered rovers to temporarily shut down until the skies clear. The planet's polar ice caps contain enough water that, if melted, could cover the entire planet in an ocean several meters deep. This frozen reservoir, along with underground ice deposits, makes Mars a prime candidate for future human exploration and, potentially, colonization. Recent discoveries have shown that liquid water may still occasionally flow on the surface in the form of briny seeps, though this remains a subject of scientific debate. Perhaps most intriguing is the question that drives much of our Martian exploration. Did life ever exist there? With mounting evidence of past habitable conditions, Mars represents our best chance of discovering whether life evolved independently elsewhere in our solar system. The search for biosignatures, chemical or physical evidence of past or present life, continues with each new mission to the Red Planet. NASA's Curiosity and Perseverance rovers have found organic molecules in Martian soil and rocks, though these could have been formed by non-biological processes. The detection of methane in Mars's atmosphere has further fueled speculation about possible biological activity, since methane on Earth is often produced by living organisms. Mars has been visited by more spacecraft than any other planet beyond Earth. From the first successful Mars flyby by NASA's Mariner 4 in 1965 to the current fleet of orbiters, landers, and rovers, we've been systematically uncovering the secrets of the Red Planet for over half a century. The exploration of Mars continues to evolve with ambitious new missions. NASA's Perseverance rover is collecting samples for eventual return to Earth, which will allow scientists to study Martian materials with the full range of laboratory techniques unavailable on Mars itself. China's Tianwen-1 mission and the UAE's Hope orbiter joined the international fleet at Mars in 2021, bringing new perspectives and technologies to bear on Martian exploration. Future plans include sending humans to Mars, possibly as early as the 2030s. Such missions would face enormous challenges: the months-long journey through space, the radiation exposure, the need to produce food, water, and oxygen on the Martian surface, and the psychological effects of isolation far from Earth. Yet the scientific and exploration potential of having humans on Mars could justify these risks and challenges. As we continue to study Mars, we're not just learning about another planet. We're gaining insight into Earth's own history and possible future. Mars serves as both a warning about how fragile planetary habitability can be and an inspiration for humanity's future as a multiplanetary species. No tour of extreme planets would be complete without Saturn, the jewel of our solar system. While all gas giants have ring systems, Saturn's rings are in a class by themselves, stretching 175,000 miles from edge to edge, yet with a thickness of just 30 feet in some places. This remarkable structure would be proportionally thinner than a sheet of paper if scaled down to the size of a typical classroom globe. These magnificent rings aren't solid structures, but rather billions of ice particles ranging from microscopic dust to house-sized chunks, all orbiting Saturn in a cosmic dance choreographed by gravity. The particles within these rings collide at speeds up to 50,000 miles per hour, creating a dynamic system constantly reshaping itself. From far away, Saturn's rings look like a single flat disk, but in reality, they are made up of thousands of small rings that are only a few miles wide each. When the Cassini probe explored the Saturn system, it revealed that the rings are far more complex than previously thought. The probe found intricate features including waves, spokes, and braided structures within the rings. Scientists discovered that Saturn's moons, particularly the shepherd moons that orbit near the rings, play a crucial role in maintaining the structure of the rings through their gravitational influence. Like Jupiter, Saturn is a massive gas giant composed primarily of hydrogen and helium. Its distinctive yellowish appearance comes from ammonia crystals in its upper atmosphere, and its winds are among the fastest in the solar system, reaching speeds of 1,100 miles per hour at the equator. These powerful winds create the subtle banded structure visible in Saturn's atmosphere, though the bands are less pronounced than Jupiter's. Saturn's density is so low that if you could find an ocean large enough, the entire planet would float on water. In fact, Saturn is the only planet in our solar system with a density less than water. This extraordinarily low density is a result of its composition, primarily lightweight hydrogen and helium, and its rapid rotation, which causes the planet to bulge at the equator. This gas giant is essentially a miniature solar system in its own right, with over 80 known moons orbiting around it. Each of these moons tells its own fascinating story, from tiny, irregularly shaped rocks to worlds larger than the planet Mercury. The most fascinating of these moons is Titan, the second largest moon in the solar system and the only moon with a substantial atmosphere. This atmosphere is actually denser than Earth's and contains complex organic chemistry, the building blocks of life. Titan's atmosphere is composed primarily of nitrogen, like Earth's, but with methane instead of oxygen as the second most abundant component. Radar imaging from the Cassini mission and data from the Huygens probe, which landed on Titan in 2005, revealed lakes and seas on Titan, not of water, but of liquid methane and ethane. Imagine rain, rivers, and oceans made of the same compounds we use as fuel on Earth. Titan experiences seasons and weather patterns similar to Earth's, with methane rain, erosion, and sedimentary processes creating a landscape eerily familiar, yet utterly alien. Another remarkable moon is Enceladus, which, despite its small size, harbors a subsurface ocean beneath its icy crust. Cassini discovered massive geysers erupting from cracks near Enceladus's south pole, shooting water ice and organic compounds into space. These plumes contribute material to Saturn's E-ring and provide a tantalizing opportunity to sample the subsurface ocean without having to drill through the ice. Analysis of the plume material has revealed the presence of molecular hydrogen, which on Earth can be used as an energy source by certain types of microorganisms, making Enceladus another potential habitat for extraterrestrial life. Saturn's rings might not be a permanent feature of the planet. Based on their composition and brightness, scientists believe the rings may be relatively young, perhaps only 100 million years old, which is quite recent in astronomical terms. They might have formed when a large moon or comet ventured too close to Saturn and was torn apart by the planet's gravitational forces. The rings are also gradually disappearing as ring particles rain down onto Saturn under the influence of the planet's gravity and solar radiation. In another 100 million years or so, Saturn's magnificent rings might be gone. Saturn also experiences some of the most powerful storms in the solar system. Approximately every 30 years, a massive storm known as the Great White Spot erupts in Saturn's northern hemisphere, encircling the entire planet. These storms are thought to be caused by seasonal changes in Saturn's atmosphere as the planet orbits the Sun. The exploration of Saturn has revealed a world of extraordinary beauty and complexity. From Pioneer 11's first flyby in 1979 to the comprehensive Cassini-Huygens mission that spent 13 years studying the Saturn system, our understanding of this magnificent world has grown exponentially. Cassini's dramatic grand finale in 2017, which included 22 daring dives between Saturn and its innermost ring before the spacecraft plunged into Saturn's atmosphere, provided unprecedented data about the planet's interior structure, the mass of its rings, and the composition of its atmosphere. Saturn's magnetic field, while not as strong as Jupiter's, is still thousands of times more powerful than Earth's. Like Jupiter, Saturn generates substantial internal heat, radiating more energy than it receives from the Sun. This internal heat source, combined with its rapid rotation, a Saturn day is just 10.7 hours, drives complex weather patterns and contributes to the planet's distinctive appearance. As we continue to analyze the wealth of data from the Cassini mission and plan future explorations of the Saturn system, this magnificent ringed world continues to surprise us. From its dynamic rings to its diverse family of moons, Saturn represents one of the most complex and beautiful planetary systems in our solar neighborhood, a true Lord of the Rings. Continuing our journey into the outer solar system, we encounter one of the strangest planets of all, Uranus. While most planets spin like tops with their axes roughly perpendicular to their orbits, Uranus lies on its side, rolling along its orbital path like a barrel. This extreme tilt of 98 degrees likely resulted from a catastrophic collision with an Earth-sized object early in the solar system's history. The impact was so violent, it literally knocked the planet sideways, creating one of the most unusual rotation patterns in our planetary neighborhood. This cosmic crash fundamentally altered the planet's evolution and gives Uranus a unique place in our solar system's history. Uranus appears as a featureless blue-green sphere due to methane in its atmosphere that absorbs red light. But beneath this calm exterior lies an alien world of extraordinary conditions. The planet's upper atmosphere is one of the coldest places in our solar system, reaching temperatures of -371 degrees Fahrenheit, or -224 degrees Celsius, cold enough to freeze most gases into solids. Unlike Jupiter and Saturn, which are primarily composed of hydrogen and helium, Uranus, along with Neptune, is classified as an ice giant. Its interior contains a higher proportion of water, ammonia, and methane ices, along with a rocky core. This different composition reflects where and how Uranus formed in the early solar system. Farther from the Sun, where these compounds could condense into solid form. What makes Uranus truly bizarre is its magnetic field, which is tilted 59 degrees from its axis of rotation and offset from the planet's center. This creates a corkscrew-shaped magnetic field that tumbles asymmetrically as the planet rotates, unlike anything else in the solar system. This strange configuration suggests that the magnetic field is generated not near the planet's core, as on Earth, but in the upper layers where partially ionized water and ammonia create a conductive fluid. The sideways orientation of Uranus creates extreme seasons unlike anything we experience on Earth. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. Imagine 4 decades of daylight, followed by 4 decades of night. This unusual seasonal pattern, combined with Uranus's great distance from the Sun, creates one of the most extreme climate systems in the solar system. Uranus has a system of rings, though they're much fainter and less spectacular than Saturn's. First discovered in 1977, when astronomers observed Uranus passing in front of a star, these rings are narrow, dark, and composed primarily of dust-sized particles and larger chunks up to several meters across. Unlike Saturn's bright icy rings, Uranus's rings contain a significant amount of dark material, possibly organic compounds processed by radiation, giving them a charcoal-like appearance. The planet hosts 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, show evidence of complex geological histories. Miranda, in particular, has one of the strangest surfaces in the solar system, with features that look like they were pieced together from completely different moons. Massive fault canyons, terraced layers, and various surface textures suggest a violent past, possibly including a catastrophic disruption and reassembly early in its history. Uranus has only been visited once by a spacecraft. NASA's Voyager 2 flew by in 1986, providing our only close-up images of the planet and its moons. This brief encounter revealed a surprisingly dynamic world. Despite initial appearances of a smooth, featureless globe, enhanced images showed cloud structures and atmospheric bands. Recent observations using advanced Earth-based telescopes have revealed that Uranus is more active than previously thought, with massive storms occasionally erupting in its atmosphere. One of the enduring mysteries of Uranus is why it emits so little heat from its interior. While Jupiter, Saturn, and Neptune all radiate significantly more heat than they receive from the Sun, Uranus's heat emission is much lower. This thermal anomaly might be another consequence of the giant impact that tilted the planet. Perhaps the collision altered Uranus's internal structure in ways that prevent heat from flowing to the surface efficiently. The exploration of Uranus remains one of the major gaps in our reconnaissance of the solar system. Planetary scientists have proposed sending an orbiter to study Uranus in detail, which would revolutionize our understanding of ice giants, a class of planets now known to be common around other stars. Such a mission could help answer questions about how Uranus formed, how it evolved after the Great Impact, and what processes drive its unusual magnetic field and atmospheric dynamics. As we learn more about Uranus, this sideways world continues to challenge our understanding of planetary physics and evolution. Its extreme axial tilt, strange magnetic field, and unique moons make it one of the most fascinating and least understood planets in our solar system. A true cosmic oddball waiting to reveal its secrets. The final planet in our tour is Neptune, the most distant of the 8 planets from our Sun. This ice giant, similar in size and composition to Uranus, reveals itself as a striking azure blue world when viewed through telescopes, a color so intense it seems almost artificial. This vivid blue comes from methane in Neptune's atmosphere absorbing red light, but the exact reason for Neptune's more intense blue color compared to Uranus remains something of a mystery. What makes Neptune remarkable are its winds, the fastest in the solar system, reaching supersonic speeds of 1,200 miles per hour. These ferocious winds drive massive storm systems across the planet, including the famous Great Dark Spot, observed by Voyager 2 in 1989, a storm comparable in size to Earth itself. Unlike Jupiter's Great Red Spot, which has remained stable for centuries, Neptune's dark spots are transient features that form, evolve, and dissipate over periods of years or decades. Despite being 30 times farther from the Sun than Earth, Neptune generates 2.6 times more heat than it receives from the Sun. This internal heat source drives Neptune's extreme weather and makes it a surprisingly dynamic world, despite its great distance from our star. The source of this internal heat is thought to be leftover energy from Neptune's formation, possibly enhanced by the separation of helium from hydrogen in the planet's interior. Neptune's atmosphere is arranged in bands of clouds at different altitudes, with some of the highest clouds casting shadows on the layers below. These high-altitude clouds are composed of methane ice crystals, which appear white against Neptune's blue background. Below these visible clouds lies a thick atmosphere of hydrogen, helium, and methane, which gradually transitions to a mantle of water, ammonia, and methane ices. Like Uranus, Neptune has a highly tilted magnetic field, offset by about 47 degrees from its rotation axis. This suggests that both ice giants generate their magnetic fields in a different way than the gas giants Jupiter and Saturn or terrestrial planets like Earth. The magnetic field likely originates in a thin layer of electrically conductive fluid somewhere between the core and the visible atmosphere. Neptune has 14 known moons, the largest of which is Triton, one of the most fascinating objects in the solar system. Triton is one of the coldest objects in our solar system at negative 391 degrees Fahrenheit, or negative 235 degrees Celsius. What makes Triton particularly strange is that it orbits Neptune in the opposite direction of the planet's rotation, a retrograde orbit that suggests it was captured by Neptune's gravity rather than forming alongside it. Triton is geologically active despite its extreme cold, with nitrogen geysers erupting from its surface and a thin nitrogen atmosphere. When Voyager 2 flew by in 1989, it observed dark plumes rising up to 5 miles above Triton's surface. These geysers are thought to be driven by solar heating, which warms the transparent nitrogen ice enough for some to sublimate into gas, building up pressure that eventually erupts through the surface. Triton's surface is a complex mix of different types of ice: nitrogen, water, carbon dioxide, and methane, creating a landscape unlike anything else in the solar system. Features called cantaloupe terrain consist of irregular dimples and depressions, while other regions show evidence of cryovolcanism, where water mixed with ammonia erupts from the interior and freezes on the surface. Perhaps most intriguing is Triton's fate. It's gradually spiraling closer to Neptune and will eventually be torn apart by tidal forces when it reaches the Roche limit in about 3.6 billion years. This destruction will create a spectacular ring system around Neptune, perhaps even more impressive than Saturn's rings are today. Neptune's other moons are much smaller and less well studied. Most are irregular in shape and likely captured asteroids rather than objects that formed alongside the planet. The inner moons are affected by Neptune's gravity and magnetic field, with some showing evidence of being reshaped by tidal forces. Like its ice giant sibling Uranus, Neptune has a system of rings, though they're even fainter and harder to observe. These rings are composed of dust particles and small rocks, with some sections appearing to clump together in strange arcs rather than forming complete rings. The origin of these partial ring arcs remains an outstanding mystery in planetary science. Neptune has only been visited once by a spacecraft. Voyager 2's flyby in 1989 provided virtually everything we know about the planet from close observation. This brief encounter revealed a surprisingly dynamic world with complex weather patterns, a system of rings, and fascinating moons. Modern observations using the Hubble Space Telescope and large ground-based observatories have continued to monitor Neptune, revealing changes in its cloud patterns and storm systems. In 2018, a new great dark spot was observed, confirming that these massive storm systems regularly form and dissipate in Neptune's turbulent atmosphere. Neptune represents the current edge of our planetary system, since Pluto's reclassification as a dwarf planet in 2006. Its discovery in 1846 was a triumph of mathematical prediction. Astronomers observed perturbations in Uranus's orbit and calculated that they must be caused by the gravitational pull of an as-yet undiscovered planet. When telescopes were pointed to the predicted location, Neptune was found almost exactly where mathematics said it should be. As we consider future exploration of our outer solar system, Neptune remains one of the most compelling destinations. A dedicated orbiter mission could reveal countless secrets about ice giant formation and evolution, atmospheric dynamics in extreme environments, and the complex interactions between a planet and its moons and rings. As we conclude our journey through the most extreme and fascinating planets in our solar system, it's worth reflecting on what we've learned. Each world we've visited represents a unique laboratory of physics, chemistry, and planetary evolution, from the hellish inferno of Venus to the windswept ice giants of the outer solar system. These diverse worlds help us understand our own planet better. Earth exists in a delicate balance, not too hot, not too cold, with just the right atmosphere and magnetic field to support the incredible diversity of life we see around us. By studying our planetary neighbors, we gain perspective on how fortunate we are and how carefully we must protect our cosmic oasis. We've seen how similar starting conditions can lead to radically different outcomes. Earth and Venus, similar in size and composition, evolved along dramatically different paths, one becoming a haven for life, the other a vision of cosmic hell. Mars once had flowing water and perhaps even life, but its small size led to the loss of its protective magnetic field and most of its atmosphere. The gas and ice giants reveal to us the complex dynamics possible in planetary atmospheres. Jupiter's centuries-old storms, Saturn's magnificent rings, Uranus's bizarre axial tilt, and Neptune's supersonic winds all demonstrate the incredible diversity of planetary systems even within our own cosmic backyard. The moons of these planets are fascinating worlds in their own right. From the volcanic inferno of Io to the subsurface oceans of Europa and Enceladus, from the methane lakes of Titan to the nitrogen geysers of Triton, these moons represent some of the most intriguing environments in our solar system and some of the most promising places to look for extraterrestrial life. The exploration of our solar system is far from complete. Missions currently underway or planned for the near future will reveal new secrets about these extraordinary worlds. NASA's Europa Clipper will investigate Jupiter's ocean moon for signs of life. The Dragonfly mission will land a drone on Titan's surface to study its prebiotic chemistry. New Mars rovers continue to search for evidence of ancient life on the red planet. Proposed missions to Uranus and Neptune would fill major gaps in our understanding of ice giants. Each discovery brings us closer to answering humanity's most profound questions. How common is life in the universe? Are we alone? By understanding the extreme diversity of planets in our own solar system, we gain insight into the billions of exoplanets now known to exist around other stars. Our knowledge of planets is undergoing a revolution. When many of us were born, we knew of only 9 planets, the 8 in our solar system plus Pluto, now classified as a dwarf planet. Today, we've discovered over 5,000 planets orbiting other stars, with thousands more awaiting confirmation. These exoplanets show even greater diversity than our solar system, from hot Jupiters orbiting closer to their stars than Mercury is to our Sun, to super-Earths with no analog in our solar system, to planets orbiting multiple stars or wandering through interstellar space without a star at all. This explosion in planetary discovery has transformed our understanding of our place in the cosmos. We now know that planets are common perhaps even the norm for stars. The diversity of planetary systems is far greater than we could have imagined just a few decades ago, and the potential for environments that could support life seems greater with each new discovery. So the next time you gaze up at the night sky, remember that you're looking at real places, worlds of fire and ice, storms and rings, oceans and geysers, each with its own unique story to tell. Our cosmic neighborhood is far stranger and more wonderful than our ancestors could have ever imagined, and we're just beginning to understand its mysteries. The planets of our solar system have been our companions throughout human history, visible points of light that moved among the fixed stars, inspiring wonder, mythology, and eventually scientific inquiry. Today, they continue to inspire us as we uncover their secrets and contemplate our place among them. Thank you for joining me on this journey through the most extreme planets of our solar system. If you enjoyed this exploration, don't forget to like this video and subscribe to our channel for more cosmic adventures. Until next time, keep looking up.